Okay everyone, welcome back. Last week we got really good at antidifferentiation by substitution, and this week we're going to get more good. I think that this is one of the most important skills in calculus to have, and I haven't actually explained why it's so important yet, but oh yeah, it's important. And we need to get really good at it, and it's pretty hard, so we need to do a lot of practice. This is all about pattern recognition. I think you just get better and better. And then everyone gets really good eventually. Let's do a problem. Here's what we're doing. We're taking there's this 8-page packet called Antidifferentiation by Method of Substitution. It's the packet that I usually use to teach this topic, although I don't know if that's a good idea, because I think it's objectively harder than the previous packet. So I moved it around this year. Anyway, page 1 we sort of talked about already, so we're jumping right to page 2. So page 2, number 4, x over root 1 minus 4x squared, and here's the problem. So I'm going to do perhaps half of these, maybe a little bit more than half, and then whichever ones I don't do are for homework. And then we're going to skip page 8 because it's not that important. And then that's all. Okay, what's going on? Well, we have to antidifferentiate x over root 1 minus 4x squared. How are we going to do that? Well, it looks like some chain rule happened here. And so, if I let u equal 1 minus 4x squared, then differentiating both sides with respect to x gives me negative 8x. And du is negative 8x dx. And now, looking back at this thing that we're trying to antidifferentiate, we see that we're missing a negative 8. So, if only there were a negative 8 in there, I undo the damage with a negative 1/8. And now I can perform a variable substitution. So this whole method is all about defining new variables in order to simplify the thing that you're antidifferentiating so that it's easier to do. And so what do we end up with? Negative 1/8 times negative 8x dx is just precisely du over root u. And now things are far simpler, and I can rewrite this in antidifferentiation friendly form. This is really just u to the negative 1/2, and now this is just an easy problem. And so we're undoing the chain rule by forcing this to be an easier function, so we can differentiate it according to some known rule, which here it is to go up a power to 1/2 and divide by half, so it becomes negative 1/8 times 2u to the 1/2 plus c. And so this whole thing is negative 1/4 times, I guess most people would just write this as root, and what is u? Well, it's 1 minus 4x squared plus c. And so that's the answer. You can even maybe double check that it's right in your head if you're willing to do that. If you differentiate this, you're going to get 1/2 times negative 1/4 is negative 1/8. This to the negative 1/2, but then back inside with the negative 8x, which is going to cancel the negative 1/8. So in my head, I have just differentiated that expression and confirmed that what I get back is the original. So that way I know I'm good. Okay, so that was a medium problem. 5 is just an easy problem. So easy that almost everyone who's not an absolute beginner would just kind of do this in one step without even thinking about it, because what is the antiderivative of cosine of something? Well, isn't it just sine of something plus c? Because the derivative of sine is cosine. Well, that's almost right, but not quite right, because the derivative of sine 5x would be, according to the chain rule, cosine 5x back inside 5. So if I differentiated this, it wouldn't quite work. I wouldn't quite get back to cosine 5x. I would get 5 cosine 5x. So now, if I just stick a 1/5 out front, well, now if I differentiate 1/5 sine 5x, I get 1/5 times cosine 5x back inside 5. And so this is just what everyone does. But if you want to be some kind of U substitution absolutist, I will support you. This problem can be done with a substitution. It's just a substitution that's simple enough that most people don't do it. You let u be 5x, then du dx is 5, of course, and so du is 5 dx. Boom, boom, boom. And, okay, yeah, I need there to be a 5 there, but there isn't one, so I stick in the 5, I undo the damage with a 1/5, and then this becomes 1/5 antiderivative cosine u du. And that's why the answer is 1/5 sine u plus c, and that's why the answer is 1/5 sine of 5x plus c. Okay, so good, choose the level that you find comfortable. Okay, number 6, this is a sort of a famous anti-differentiation problem that this came up in the previous video. So this is not your first time seeing this, but this is our first time doing it just alone. What is the antiderivative of tan x? Well, this comes up a lot. So this is something that we need to know. Some people even memorize it, but this is not necessary. Well, there's no known simple function that I encountered during the differentiation unit, which when differentiated gives me tan. And frankly, it doesn't look like some chain rule happened here, so I'm stuck. But building upon a vast body of experience with kinds of techniques that we saw last week, and we're just getting better and better at this. If I rewrite tan as sine over cosine, sort of a familiar move from pre-calculus. One of the reasons why we do endless trig identities is for moments like this, so you're experienced enough to think to do something like this. Now we see that it does look like some chain rule happened here. Specifically, the derivative of cosine is negative sine, and that's the one that I want. If you do it the other way, it doesn't work, but if you let u be cosine, then du dx is negative sine, and so du is negative sine x dx. This is the key substitution. I want there to be a negative here. There isn't, so I stick in the negative, I undo the damage of the negative on the outside, and thus I get negative antiderivative. Negative sine x dx is du over u. And this one is well known, it's natural log. That's why I end up with negative natural log absolute value u plus c. And so the real answer is negative ln cosine x plus c. And while it is perfectly fine to just leave it like that, and that's absolutely correct, no one does that, or specifically textbooks and stuff don't, because it's considered like not cool or something to have a negative in front of your natural log, because that negative can be thought of as -1, which can be popped up via a log rule, and that's why this is really like ln absolute value cosine x to the -1, and so really this is ln absolute value secant. And so, yeah, you're just gonna see the antiderivative of tan listed as ln absolute value secant for that reason. Okay, let's do one more before I have to erase. This is another I think just really hard problem. Antiderivative cosine cubed. Here, it just doesn't, frankly, in my opinion, look like any chain rule happened here. You can rewrite this as cosine x quantity cubed, and maybe that makes the problem even more sort of obviously bad. If you let u be cosine, which is kind of what you want to do, then du dx is negative sine, but there's just no negative sign anywhere to be found, and so it just doesn't appear that you can push forward with this problem at all. And actually, one benefit of the u substitution, it's not just that it makes it easier for you to do the problem, which it does. It also sort of forces you, I kept referring last week to it as sort of bookkeeping. It sort of forces you to check as you're going that you're sort of doing the problem correctly, because it forces you to sort of do a substitution. It forces you to find the the sinx in here, and since it isn't there, in some ways you can think of use substitution as also sort of not letting you make a mistake, so to speak. Okay, what can we do now? Well, here's where you just have to be bold and creative, and you know, get that toothpaste back in the tube somehow, as I talked about in last week's video. What can we do? Well, one thing we can do, not sure if some of you would have thought of this yourself or not, but you can think of cosine cubed as cosine squared times cosine. Alright, why would I want to do such a thing? I want to do such a thing because cosine squared is 1 minus sine squared. So now I get 1 minus sine squared cosine. And now that can be split up into two separate problems. The antiderivative of cosine minus the antiderivative of sine squared x cosine x dx. And here I had to sort of think to perform this kind of a trigonometric manipulation and an application of trig identities. But now hopefully you should be feeling good, because now it does look like some chain rule happened here. Specifically, cosine is the derivative of sine. So to solve just this problem here, if I let u be sine x, then du is cosine x dx. That's a step that people often do in just one step like that. So therefore this is really just negative u squared du, and therefore equal to negative 1/3 u cubed plus c, if you're following this. So yeah, you let u be sine, that's really like u squared du, and that's the antiderivative of u squared. And so the antiderivative of cosine is sine, because the derivative of sine is cosine. And so as a final answer, we get sine minus 1/3, and u is sine here, so that's sine cubed x plus c. And that's the final answer there. Woo! Okay. Good. Yep, that's just right. Okay. More. Woo. Let's do it like this. Okay. Next, number 8. Number 8 says, what is the antiderivative of x squared over x cubed plus 5? Okay, this is a certain thing to kind of just be looking out for. This is a rational function, but the degree of the numerator is less than the degree of the denominator. 1 less, specifically. And, okay, we know that when you differentiate polynomials, you get a new polynomial with just 1 degree less. So wouldn't it be great if the derivative of x cubed plus 5 were x squared? And the answer is, it almost is. So after a while, it does look like some chain rule happened here, because if I let u be the bottom, x cubed plus 5, then du dx is 3x squared, and so du is 3x squared dx. Okay, therefore I need a 3 here, and so I put a 1/3 on the outside to cancel out. That's that 3. And this problem can thus be reduced to 1/3. 3x squared dx is du, and on the bottom here is u. This we know to be 1/3 ln absolute value u plus c, and so this is 1/3 ln absolute value x cubed plus 5 plus c. So that was relatively easy. I guess we did problems like that before. Okay. At some point I'm gonna stop and let you figure. Oh, here we go. Here's 9. This is also a rational function, but it's harder. A little bit. Uh-oh, baby's awake. X squared plus 2 over x squared plus 1. Okay, and here you might try in vain to come up with some creative substitution which enables you to make progress on this, but really we should follow the principle of, I think I talked about this already last week, we should follow the principle that it's easier to antidifferentiate something which has been broken up into lots of little pieces. And so even if it's getting more complicated, if it's getting broken up into smaller little pieces, then it's typically going to be easier to antidifferentiate. And we know that all rational functions can be broken up into smaller, more manageable pieces by doing polynomial long division. So when it comes to antidifferentiation, you should always do polynomial long division. You should do polynomial long division literally whenever you can. You should do it. And so we can of course do it here, right? X squared plus 2. You can even just do this in your head, but I'll just do it. Divided by x squared plus 1 goes in, well, one time, and then leaving a remainder of 1. That means that this problem should really best be thought of as 1 plus 1 over x squared plus 1. And now things have been broken up into smaller pieces. Does that make it easier to deal with? Well, in this case, yes, absolutely, because the antiderivative of 1 is just x, and the antiderivative of 1 over x squared plus 1 is just arctan. So in this case, we got lucky or something, and the problem turned out to be kind of easy. Okay, I am going to leave 10, 11, 12, 13, 14. I'm just going to leave all the next bunch of chunk to you. Not that they are obviously necessarily easier, but they are doable. And we are going to skip ahead to 19. Okay. Oh boy. Very sad, baby. Okay. 19. Well, it's just a direct follow-up on what we did a minute ago. But it's a case in which things don't work out quite so easily. Antiderivative of x cubed plus 1 over x squared plus 4. What should we do? Well, after you've seen enough problems, you just know what to do based on experience. And here experience tells you it's a rational function. All rational functions, whenever you're antidifferentiating them, you should do polynomial long division whenever you can. So whenever the degree of the numerator is greater than or equal to the degree of the denominator. So we just get ready to do polynomial long division with x cubed. So the organized way to do this is like this. I think you basically have to do that. We divide by x squared plus 4, and then we just go. Maybe I switch colors for this, although you can't always see the colors. X squared goes in x times, so that's x cubed plus 4x, boom boom, so that's negative 4x, and then this is plus 1, and then already the algorithm just terminates, because you can't go any further. Okay, so what have we just accomplished? Well, we just did some preliminary algebra basically. And what we found, what we found is that this is really x plus negative 4x plus 1 over x squared plus 4. Okay, well, is that better? I guess it's a little bit better because now I know how to antidifferentiate x, of course. Do I know how to antidifferentiate negative 4x plus 1 over x squared plus 4? Well, looking back on the previous problem, isn't it true that the derivative of a quadratic is a linear? So perhaps we could hope for the derivative of x squared plus 4 to be negative 4x plus 1, give or take a constant, in which case we could handle it that way. But it doesn't quite work, right? Because what is the derivative of x squared plus 4? It's 2x. So this 1 is just out of place, basically. It's just kind of not working. Well, what we now do is we further split it up. So we rewrite this as x, and I'll split up the problem now, minus 4 x over x squared plus 4, and then just plus 1 over x squared plus 4. Okay, so not only polynomial long division, but also recognizing that we can split up this numerator, which is 2 terms, into 2 separate antiderivatives. And this is just the way to do this problem. Why is this the way to do this problem? Well, now 2 out of the 3 of these are sort of easily doable. And okay, I'll just do them right now. This one is, of course, just 1/2 x squared. What is this? Well, now it does work to let u be x squared plus 4, because then du dx is 2x, and so du is 2x dx. And that means that that this numerator now is the appropriate sort of back and side, or at least it almost is. So I'm going to mentally split that 4 up into 2 times 2. I don't even have to do it mentally. I guess I can just do it. So it's minus 2 antiderivative 2x dx over x squared plus 4. Okay, but the point of this is that now I can do a u sub, and it becomes minus 2x dx is du, and x squared plus 4 is u. So this part turns out to be minus 2 ln absolute value u, or minus 2 ln absolute value. Actually, the absolute value is not needed because x squared plus 4 is always positive. Okay, so we're sort of like now 2/3 done or something. So now all we need to do is figure out how to antidifferentiate 1 over x squared plus 4. And this is the exact problem we did twice last week. So it's hard, but now once you've seen it, it's maybe not that hard, right? The problem is this is almost arctan, but not quite because of the 4. And so we perform this entire algorithm where we factor out a 4, rewrite that as x squared over 4 plus 1, retake the 1/4 just out entirely, then rethinking of x squared over 4 as x over 2 squared plus 1. You don't need to show quite this many steps, but if it's comfortable for you to use this many steps, then do so. Now we see that u should be x over 2, so du is 1/2 dx. And now we need a 1/2 in there. So we, depending on how you like to do this, you stick in a 1/2, you undo the damage with a 2, and thus we get plus 1/2 antiderivative du over u squared plus 1, which is arctan u. And so what we end up with is 1/2 arctan x over 2 plus c. And this whole complicated thing is the actual answer to this problem. And so yeah, it involved kind of a lot of sort of confidence over the general principles at play here. Rational function, do polynomial long division, break it up, hope that the derivative, once you've done polynomial long division, it's always going to be the case that you're going to have a polynomial in the numerator, which is a degree less than the polynomial in the denominator. And so you hope it's just the derivative of the thing in the bottom, but if it isn't, it can be further broken up. And you can kind of use your imagination to see how far this process will take you. Can you now antidifferentiate sort of any rational function, almost? No, but like almost. Okay, so good. Let's do one more. Well, I will skip around a little bit, keeping track of which ones I'm doing. So I am going to make a video. Well, I won't tell you how to live your life. You could just not watch any of these videos and do this whole packet all by yourself. I guess that would be the most bold thing. You could pause each problem and do it and then check. Keep it running in the background on mute. I don't know. I'll leave it up to you. So 20. We may have done a problem almost exactly like this. last week, and basically the gist is that you should see that this is looking very much like arcsine, and you kind of just need to know the derivative of arcsine. If I write this as dx over root 1 minus 2x quantity squared, now it's looking very much like arcsine. And so the way to go here is to let u be 2x, du is then 2 dx, I stick into, I undo the damage, and we therefore get 1/2 antiderivative du over root 1 minus u squared. And this just is the derivative of arcsine. And so this whole problem becomes 1/2 arcsine 2x plus c. Alright, so that was not so bad. 22 is a problem which also you sort of need to have some already experience with doing these problems. What does this look like? Well, to me it looks a lot like arcsecant, because the derivative of arcsecant, I simply know, is 1 over x root x squared minus 1. And so knowing that, you can look at this problem and you can say, man, if that 16 were a 1, that would be great. So let's make it a 1. Here you do have to be careful. And I don't do any shortcuts, I just do it every time. So inside the radical, I shall factor out 16. And when I do that, I get x squared over 16 minus 1. So I sort of did what I needed to do, which is I made that a 1. Now there's this 16 here, which I can just take out. And so when it comes out of jail, it becomes a 4. Of course, it's in the denominator. So this is really like 1/4 antiderivative. What was I doing? Dx over x root. And since I've already factored out the 16, I'm going to rewrite this as x over 4 squared minus 1. In preparation for doing a u-sub. But, and I think this is why doing the u-subs are really important, because they, like I was saying before, they sort of force you to do the problem correctly. If I now let u be x over 4, I see that du is 1/4 dx. And since du is 1/4 dx, I need there to be a 1/4 up here. But notice that if I intend to replace all my x's with u's, then I also need this x to be a x over 4. And so really, I'm just multiplying the denominator by a 4th, but also the numerator by a 4th. And so those two moves exactly balance each other. And that's why this turns into 1/4. The numerator is just du, sort of algebra kind of speaks for itself. And then this is u root u squared minus 1. And you sort of can't go wrong if you take it all the way down to the end. What is that? It is by definition, or well, not by definition, but it is by previously figured out rule. 1 over u squared minus 1 is the derivative of arcsecant. And that's why this is 1/4 arcsecant u, or arcsecant x over 4. And for complicated reasons, we got absolute value in here as well, plus c. Okay, that was 22. Sort of not too bad, but yeah. Okay, good. Let's do more. 23, I think, is harder. We did one like this last week. Okay. 23. antiderivative 2 over root negative x squared plus 4x. And it's hard to know sort of why or how what to do next here, but at the moment it does not look like some chain rule happened here. And frankly, I don't recognize this as being anything. And so sort of when in doubt, when you have a quadratic, you can complete the square. And so that's what I'm going to do right now. I pull out the 2 because it's not doing anything. And down here I have the square root of negative x squared minus 4x, boom, and boom. Okay, and all right. Notice I factored out the negative, but okay, it's all working out. What do I need to do? I need to put a 4 here, but what I've really just done is subtracted 4, therefore, so I need to add a 4 back in. Okay, inside the radical, inside the denominator. And thus, this becomes 2 dx over root 4 minus x minus 2 squared. Right, and here, personally, almost no one takes my advice on this, but it's good advice, I think, which is to just get rid of this x minus 2 now with a simple substitution. Du dx is just 1, so du is just dx. And so this is not too hard to do, and I think is worth it because it makes things more clear. So this is 2 du over root 4 minus u squared. Okay, now what? This is almost arcsine, problem being that this is a 4 instead of a 1. So now I go into the whole arcsine business where I'm like, okay, down here I want to do square root, factor out of 4, 1 minus u squared over 4, and then that becomes, okay, so that 4 comes out of the denominator, becomes a 2, cancels the 2 on the outside, and what we end up with is du over root 1 minus u over 2 quantity squared. Is how I choose to rewrite u squared over 4. Now I can do another substitution, so I usually go to w next because v sometimes looks a lot like u. If w is u over 2, then dw is 1/2 du. And so finally, I stick a 1/2 in here and undo the damage with a 2 on the outside, and that's why I get 2 dw over root 1 minus w squared. That is arcsine w, and that's why we get 2 arcsine w, but w is really u over 2 and u is x minus 2, so it's x minus 2 over 2 plus e.